I'm going to build this 5-inch Freestyle FPV drone and take you through the entire process from choosing and buying parts to assembly, programming and getting this flying. Anyone can do it, even beginners, and this is how I do it. By the way, this video is sponsored by SpeedyBee, T-Motor and FlyFish-RC, who have provided the parts featured in this particular build. Building a drone can be overwhelming, especially when it comes to figuring out what parts you need to buy and making sure they're compatible. To make sure that you have a smooth building process, it's important to make a shopping list of all the parts you're going to need before you begin. For every drone build, regardless of size, you're going to need the following parts. Now, after creating a shopping list, it's important to research and determine what components are best for your build. A good starting point is to look at what parts are on other 5-inch pre-built drones, but there's always one part I start with first. If you were to think of building a house, the first thing you'd actually start with is laying the foundation, and the frame is the foundation of any FPV drone. For this build, I'm going to be using the FlyFish-RC Volador DC5, which FlyFish-RC have sent to me as a sponsor of this video, but you can use any similar frame. The next component you need to choose is the flight controller and ESC. But how do you figure out if your flight controller and ESC are compatible with your frame and the rest of your build? Taking a look at the frame specifications, we can see that it has stack mounting holes for both 20x20 and 30x30 for M3 bolts. So we need to find a compatible flight controller and ESC, but how do we buy the right one? Well, the easiest way to buy the right flight controller and ESC and make sure that they are both compatible together is to buy them where they're sold as a stack. But you may come across stacks that are 30x30 as well as 20x20 to make things even more confusing. But if you want to choose a 30x30, you probably won't have any issues if you get the amp rating right. If you go down the path of 20x20, you may end up with the wrong stack, and here's how that actually happens. Some stacks can take M2 screws, and these aren't going to be compatible with our build, and they're really designed for 3 to 4 inch micros. Some of these stacks may actually appear to be compatible with a 5-inch quad, when they actually aren't. And the easy way to tell is, if you go and look at the specifications of the stack, it should tell you the size of the hole. And if it's 4 mils, that means you're on the money. And this means that we're going to get this little gummy that goes into the hole to make it compatible with our M3 stack screws. The other thing when choosing a stack is, you'll notice the mention of 45A or 50A. What this means is how many amps the ESC is rated for. And with a 5-inch freestyle build, you want to be selecting at least 45 amps to be on the safe side. There's also some other numbers that you need to know about, and you often see these represented as F405, F11, F7, and this is just the processor. If we were to imagine that the flight controller is like our desktop computer, this would just be like choosing the difference between an Intel i5 and an i7 processor, or if you're in Team Apple, M1 versus M2 Mac. For this build, which is also sponsored by SpeedyBee, I'm going to be using the SpeedyBee F405 V3 stack, and SpeedyBee have sent this to me to include in the build. Now, of course, you can use any stack that you want, just make sure you choose the right one. Now we have the two main components out of the way, the next few and final components are also important to get right, but they do depend on what gear you already have. Starting with the video system. If you already have FPV goggles for one of the digital video systems, then it's pretty obvious you need to go out and buy a compatible VTX and camera combo. But what if you're flying good old-fashioned analog? How do you choose the right video transmitter and camera? Well, let's start with the camera, which can be confusing. You're going to find mini cameras, micro cameras, and nano cameras. And let's just straight away eliminate nano cameras. But mini and micro can be hard to know which one to choose. And how do you even know which is the right one? Well, if we go back to our frame, we can see in the specifications of the frame, it tells us what the camera spacing is. And for the Volador DC5, it's 19 mils or 20 mils, which puts it in micro camera size. If we look at the dimensions of most micro cameras, we can see they're 19 mils wide, which is going to be perfect for our frame. And on this build, I'm going to be using the Runcam Phoenix 2, which SpeedyBee also sent me as part of sponsoring this video. Now we need to choose a video transmitter. The main consideration when it comes to choosing a video transmitter is the output power. And for a 5-inch freestyle build, you want a minimum of 800 milliwatts, and you can get VTXs up to 2 watts of output power. Now, I'm going to be using the SpeedyBee TX800 as part of the sponsorship of this video. But I've also used it previously on a number of other builds, especially where I upgraded the cheapest FPV drone. Now, if you're flying analog, you want to choose an antenna that's compatible with your goggles as well. And if you don't know what that is, well, chances are that it's going to be an RHCP or right-hand circular polarized antenna. And I'm going to be using the Rush Cherry MMCX as that's going to plug straight into my video transmitter. The first of the remaining components is our radio receiver. Which one you choose is going to be dependent on what radio you have. I'll be using the Radiomaster RP1, which I paid for out of my own pocket because I fly ExpressLRS. For propellers, I'm going to be using the Ethix P3.5 or Radberry props, but there's still two more critical components we haven't selected, and without them, our drone's not going to fly. Is our motors. And which motors you choose actually comes down to what batteries you already have or you're prepared to invest in. You see, for the powertrain, you need to have the right motors and the right batteries. If you already have a bunch of 4S or 6S batteries that you've used on other 5-inch drones, and you don't want to buy any more batteries, then it's really an easy choice. But if you don't have any batteries, then for a 6S setup, you probably want to be looking at around 6S 1100 mAh batteries. Or for 4S, you're going to be in that 4S 1500 mAh battery range. But your battery setup is also going to determine what motors you must get. Now, ideally for our 5-inch build, the motors you want to use to get the best performance are going to be 2207 motors. But you can also use 2306 if that's what you prefer. If you're going for a 6S setup, you want to be using 1750 kV, and for 4S, you want to go around that 2550 kV mark. T-Motor have also sponsored this video and sent me the Velox V2 motors in 2207 1750 kV for the build, and just like the other sponsor components, make sure you choose the right motors for your build. Now we've got our shopping list completely built out and all of our parts selected. It's time to go and order them. If you're in the USA or Canada, there's some great FPV stores that you want to check out. And if you're in Australia like me, there's some amazing local options. The other thing is you can also order from AliExpress. Just don't expect fast shipping. When it comes to building your FPV drone, you're also going to need the right tools. And while you're buying the right parts from an FPV store, you might as well grab all the right tools that you need. So here is a list of all the tools that you're going to need to help complete this build. Now it's time to actually get to building our quad. But if you're using a different frame, you're going to need to find a tutorial on how to assemble that. However, what I found is the best guide to assemble the Volador is from FlyFish-RC. It's only 10 minutes long and I've linked that in the description for you. After you've assembled the frame, to avoid mistakes, troubleshoot any fitment issues, I like to do a dry fit where I put all the components such as the ESC, flight controller, camera, VTX and antenna on the quad to see how they all go together. When doing my dry fit, I found two key issues that I needed to resolve. The first issue I found was that FlyFish-RC sent me an antenna where the connector actually wouldn't fit through the TPU mount. So I had to cut the TPU to be able to get it on the build. But this then highlighted another problem because I didn't have enough space to fit the angled MMCX antenna without damaging the wire. I found an antenna with a straight MMCX connector that would actually fit perfectly, so I ended up using the Rush Cherry antenna instead. With the dry fit complete, you can then choose your own adventure. You can either mount the motors first or solder up the ESC. Using the C4 tip on my TS100, I tinned each of the motor pads on the ESC. An easy way to destroy your components is from small splashes of solder spilling onto your electronics. So when you're doing any soldering, you want to approach the target from the same side and then rotate your components around you. If you're using the Volador frame, you'll need to remove the XT60 connector that comes on the battery lead included with your stack because the Volador integrates a specific XT60 into the top plate. At this point, you only need to tin one end of the battery leads that will be soldered to the ESC because you'll need to shorten the other end later on. I soldered the battery leads straight onto the ESC. Now the black wire goes to the minus pad and the red wire goes to the plus pad. To keep your build clean on the Volador, the battery leads run through a tunnel between the mid and bottom plate. And ideally, you want to feed your battery leads through that before soldering them to the ESC, as this will stop putting pressure on your ESC, which I then had to fix by reflowing the pads and wires. So you can just avoid that pain by doing it the other way around. For the capacitor, SpeedyBee included behemoth of a capacitor, 35 volts at 1500 microfarads. And on my builds, if I don't have much space, I typically use a 35 volt 470 microfarad capacitor, while on builds with plenty of room, I use a 35 volt 1000 microfarad capacitor. Now, for the capacitor to be the most effective, you want to solder this directly to the ESC pads. And the side with the stripe or color is the negative side, and this is going to go to the minus pad where the black wire is on the ESC. The other side goes to the plus or the positive side where the red wire is. Next up is the motors, and I thought this would actually be pretty straightforward, and it should be, except for the life of me, I couldn't seem to find the packet of 16 M3x10mm screws which you actually need, because FlyFish-RC include these really thick TPU skids for each arm, and you need those long motor screws. However, T-Motor did come to the rescue by including 2 sets of M3 screws with each motor, and I think the longer ones are M3x10mm, which should be perfect. With the TPU guards, they do allow you to do a little trick, which is to put all 4 bolts in with just a tip of the screw sticking out. This actually makes fixing the motor on top easier, and then you just need to tighten them up. Keep in that when you do screw the motor down, you want to screw it tight, but not so tight the screw spins in the thread. You also want to check to make sure the screw doesn't pop through the hole and touch the windings, because this can be a nightmare. They should be flush or just a little bit longer, but not too much. To make soldering the motor wires easier and keep them in place, I take them at the very end of the arm where it meets the body. And you may also want to use some kind of tape over the middle of where the heat shrink and the motor wire is met. Although some pilots simply put tape in the middle of the arm, and they use red tape. Red, disgusting tape. I'm looking at you, Bardwell. Keeping with how clean this build is, which red tape wouldn't be clean for the build, I decided to be fancy. But look, you don't have to. So I ran the wires around the standoffs and then over the ESC and then over the pads. Just don't pull the wires tight, just lay them around and then cut the ends off. I cut all 3 wires to length on the first motor, and then you need to tin each wire and solder them to the pads. For the rest of the motors, I did something a little bit different, which I actually found to work a lot better. This was lay the wire, cut it to length, tin it, and then solder each wire individually. I just found this to be a lot easier and cleaner. With all 4 motors done, and while I was still using the C4 tip on my TS100, it was time to tackle the other end of the battery leads. After feeding them up through the back of the frame and the TPU mount towards the XT60 connector, there was a little quirk I ran into, and this could actually spell disaster if you get this wrong. You see, there's 2 sides to an XT60 connector. The flat side is for positive or plus, and the curved side for negative or minus. The problem is the red wire, which runs to the positive or plus pad on the ESC, is not meant to be on the curved side of the XT60 connector, which is actually the negative side. And the black wire, it turns out to be on the positive side. And this is a problem, but there is an easy fix. Here's how. The first thing we have to do is make sure the red wire comes up past the top of the TPU mount that the XT60 connector sits on. Then we're going to cut that red wire to length. Now we feed the red and black wires back through so they come out the bottom of the frame, and then we cut the black wire to match the length of the red one. But there's still a couple more steps to get this 100% right and avoid toasting our quad when we plug a battery in. First, we need to cut off a small amount of the silicone covering, just exposing a little bit of wire. Now we're going to tin these ends of the wires, and you may need to do it from both sides to make sure there's plenty of coverage. Do this for both the red wire and the black wire. Now, cut off a small length of heat shrink, 1 for each wire, and feed them over the wire and push them down as far as away from the heat as possible. Take that XT60 connector and tin it. I use blue tack to hold it in place, remove the rear standoff by undoing the screws, and then solder the red wire to the flat side and the black wire to the curved side. Once that's done, push through the heat shrink and use a cigarette lighter or heat gun just to shrink that down, covering all of that soldering we've just done. Putting the connector back towards the ESC over the mid plate with a small twist in it to ensure the connector was facing the right way. The next part was actually a pain in the butt for me later on in the build, and you can actually benefit from my hindsight. To make feeding the VTX and the antenna easy, now is actually the best time to feed the antenna connector between the red and black wires for the battery lead, and then connect it to the VTX before putting the rear standoffs with the TPU back on the quad. But you can solder up the VTX now, or if you're like me, we can go and do the camera. On the Runcam Phoenix, you'll notice a red, black, and yellow wire that leads to a plug, as well as a loose blue wire. And then you've got this blue and black wire leading to a plug. Now, we're going to ignore those for now. We now need to check our flight controller for a pad with CC on it. This is camera control. The SpeedyBee flight controller in this particular build has that pad. But if your flight controller doesn't, you can just cut the blue wire off. Take the loose blue wire, the red and black and yellow wires, and we're going to make those 4 wires into one group by grabbing and twisting them. Go to your flight controller. There should be a pad with the letters CAM, C-A-M, VI or VIN, VIN. And there's also going to be a 5V and G&D pad or ground pad near them. To work out how long the wire from the camera to the flight controller needs to be, gently pull it towards those pads on the flight controller, keep some slack on the line, and you want it to be a little longer than shorter. Cut the wires and strip back a small amount of the silicone to expose the internal wires, and tin them away from your flight controller. The amount that you want to expose or have tinned should be no bigger than the pad you're going to be soldering it to. From here, we're going to tin the CAM, 5V, G&D, and CC pads on the flight controller. I find it easier to work right to left when soldering the wires to the pads, so the red wire is going to go to the 5V pad or 5V pad, black wire to G&D or ground, yellow wire to CAM or VIN, and the blue wire to CC. With the camera being wired up to your flight controller, it's kind of useless if the drone can't transmit the video signal. So now we need to wire up the VTX. To find where we need to solder the VTX to, look for the VTX pad. You should also see some other pads near it, such as 5V, BAT or VCC, and 9V or 9V, as well as ground and some pads with the letter T and the letter R with a number next to each of them. This is where we're going to need to solder the VTX, but we do risk blowing up our VTX if we use the wrong pads, and that is not a good thing. If you've bought a different VTX to the SpeedyBee TX800, you need to check to see what power input it can take. You see, some VTXs can only take 5V of power, like the SpeedyBee TX800. Well, others can actually take up to 36V, like Foxy's Reaper Extreme, or the DJI FPV system, both preferred 26V. Tin the nearest G&D pad, the VTX pad, and the power pad that is right for your VTX. For the TX800, we're going to be tinning the 5V pad. Like we did with the camera wires, by twisting them and working out the right length, do the same with the VTX wires. Take the red wire and solder that to the power pad that you've just tinned, and make sure that you're not wiring it to a pad that sends a higher output power than what your VTX can handle, otherwise it's going to blow. Then black wire to G&D or ground, yellow wire to VTX, and the remaining color wire, whatever that is, which is green on the TX800, that goes to the T pad with a number next to it. In my case, that's T1, which is the transmitter pad on UART1. We're going to need this later on because this is going to allow us to change the channel using our flight controller on our VTX. If you're using the SpeedyBee TX800 VTX, you're also going to need some extra parts that aren't included in the frame kit to mount it. To mount the VTX, put the screws through the 20x20 mount spacing that's underneath the VTX area on the frame, and put the M2 hex nut on when the screws start to show through a little bit. You may need to use pliers to hold the M2 hex nut while you push through the rest of the screw. Put the M2 nylock nuts from the frame kit on top of the VTX to secure it. Now, to keep it secured and centered, I actually put them upside down as the hole for the VTX is kind of large. Now all you need to do is wire up your receiver. I'm going to be using the Radiomaster RP1, which is an ExpressLRS receiver. However, this is the same process for Crossfire, Ghost, and Tracer. The first thing we need to do is tin the pads on the receiver, and there's two sides. I'm going to be using the side that has the labeled pads just because it's going to be a little bit easier in terms of the build. Most receivers do come with wire, however the Radiomaster RP1 didn't, so I'm using my own 26 gauge silicone hookup wire. So going to cut some decent lengths and strip back and tin the ends of the wire. Then we simply need to solder the wires to the pads. Now the side I'm soldering to is the back side, which is labeled, so it makes it really easy. The first pad is ground, second is 5 volt, TX and RX. Now we're going to feed through the antenna in between the power leads and stick the ends of the antenna through the antenna mount in that TPU bracket. Once that's fed through, we're now going to take our receiver and connect the UFL connector onto that receiver. We're now going to take the heat shrink that was in the packet, feed that over the wires and then over the receiver and over the TPU connector, and then use a cigarette lighter to shrink it down. This is going to keep everything nice and secure. I found the easiest way to mount receivers is to use double-sided mounting tape, and in this instance I'm just going to stick it on top of the VTX. Once that's done, you now need to twist the wires to put them into a group, and now we need to go and look at our flight controller as to which pads we're going to mount them to. I'm going to be using the 4.5 volt ground T6 and R6 pads that are at the back of the flight controller. The other thing is you don't want to run the wires over the flight controller as their movements and vibrations can interfere with the gyro. We're going to cut the wires down to size, remove a bit of the tip of each wire in order to then tin it. Then we need to tin the pads on the flight controller and then solder the wires. Starting with the red wire to the 4.5 volt pad, black to ground, the white wire is going to go to T6 and the blue wire is going to go to R6. And now the build is complete, there's one thing we need to do to make sure this doesn't go up in smoke. And I mean that literally. And that's test it with our smoke stopper. So I've plugged it in, now it's time to flick the switch and hope the light doesn't come on. And bingo, we're in business. Now it's time to program and tune your drone. For the next part, I'm going to assume that you already have Betaflight and you're not taking on a build as your first foray into FPV. To make sure your quad flies the best it possibly can, it needs to be running the latest version of Betaflight. After plugging it into your computer, head to the Update tab. To use the right firmware target for your specific flight controller, select Auto Detect. This is going to prevent you from flashing the wrong configuration to your flight controller and possibly bricking it. Then press Load Firmware Online and flash firmware. After this is done, apply custom defaults, and now it's time to configure Betaflight. It's not as scary if you know what you're doing, and I'm going to guide you through it. While we're on the Setup tab, place the quad on a flat surface and click Calibrate Accelerometer. So it's going to take a few seconds, but once that's done, we should be able to pick up our quad and rotate it where the model on the screen follows our movements. If it doesn't, you need to check the arrow on your flight controller as to which way it's pointing and make note of that because we're going to take care of that in a second on the Configuration tab. But first, it's over to the Ports tab. For the SpeedyBee flight controller, it already has UART4 ticked for MSP, and this is because you can actually use the SpeedyBee app on your iPhone or Android device to configure the flight controller, which is pretty handy to make changes out in the field. You also want to leave MSP ticked for USB, otherwise you're not going to be able to connect your flight controller back to Betaflight. Looking at our flight controller, check out the T and R pad that you soldered your receiver to. For me, I used T6 and R6. Now we're going to go and tick the serial RX box for UART6. This is going to enable our receiver in Betaflight so we can actually configure that a bit later on and send radio commands to the flight controller to be able to fly our drone. For your VTX, if you're also using analog, the flight controller can tell the VTX what channel and output power to be on. So take a look at your flight controller and see what T-pad you soldered the color wire to. For me, that's T1, which is UART1. In the peripherals column, you'll see in the drop-down there are 3 VTX options. Now you're going to need to check your VTX manual as to whether it uses TBS Smart Audio or IRC Tramp. The TX800 VTX that we're using uses IRC Tramp, so that's what we're going to select. But if you went with DJI HD0 or Walk style, you're going to need to tick MSP for the UART or TNR pads that you wired it to, as well as select MSP display port from the peripherals column for that particular UART. Now it's time to hit save and reboot. Connect back to your flight controller and head to the configuration tab. I'm going to make this part really simple because I know it can seem overwhelming at first. The first thing we need to know is our gyro update frequency. Can we actually change it between 8K, 4K, 6K and a bunch of different settings? Or is it actually locked to 3.2 kHz? Now, if it's not locked and your flight controller is an F7, set it to 8K for gyro and 8K for PID loop. While it's an F411 or an F405, set it to 4K and 4K. But if the gyro is locked to 3.2 kHz, don't change anything, you're all good. Now, the SpeedyBee flight controller we're using also has a really cool feature, and that can tell you your altitude or how high you are, because it's got an onboard barometer. So if this is ticked, leave it on. Think back to the setup tab a few moments ago. When you moved the quad, did the model on the screen follow it exactly? If it didn't, well, this is where you're going to need to change the gyro board alignment to match the orientation of your flight controller. So you might need to swap that around. Now we get to personalize our quad just a little bit by setting the craft name and the pilot name. You can leave the camera at 0 or change it to 20 if you want. And to make sure that when you crash, you can actually turtle out of that crash, set the maximum arm angle to 180 degrees. In the other features, make sure air mode is turned on as well as OSD, if it isn't already. And while you don't need to select any of the other options, if they're on by default, it's just best to leave them. Your motors can act as a beacon if your quad goes down and the battery is still connected, so turn on RX Lost and RX Set in the DShot Beacon Configuration tab. The same function works for the motors to act as a beeper. I turn off everything except for the following: RX Lost Landing, and RX Set. Now, once you've done all of that, hit save and reboot. Time for the receiver tab. For this next part, you're going to need to turn on your radio transmitter. Set your receiver to serial UART, and if you're using ExpressLRS or Crossfire, for the serial receiver provider, set it as CRSF, and then turn telemetry on. If you're using IRC Ghost or FreeSky, set that accordingly. We still have some more configuration to do on this tab, but first we're going to hit save and reboot, and then we're going to come back to this receiver tab. If your receiver is not already bound to your radio, now's your chance to go and do it, and you probably need to watch another tutorial as we're going to skip over how to do that in this particular build. Now, if your receiver is bound to your radio and you move the gimbals on your radio and flick the switches, the different channels on the screen should move. So when you move the throttle on your radio, the throttle channel should also move. But if it's another channel moving, then you're going to have to change your channel map to match. I find the easiest way to work this out is to grab your radio and go to the Mixes tab. Then look at the order of the channels in that list. Mine is A for roll, T for throttle, E for pitch, and R for yaw, in that order. So my channel map is ATER1234, but yours may be a little bit different. So change it around, and then once it's all lined up and working correctly, hit save and reboot. To make your quad fly, activate the beeper, turtle mode out of a crash, we need to configure what the switches on our radio activate from the modes tab. You're going to need to at least use the arm for any quad. So click add range and then flick the switch you want to use for arming and set it to the position that you'd also like it to be at when the quad is armed. Then adjust the yellow sliders to appear over the yellow marker. Do this for all the other functions in Betaflight that you want your quad to be able to do when you're flying it. I find the most important ones to me are beeper makes the motors beep so I can find my quad if it's downed. Flip over after crash allows me to turtle mode out of a crash. VTX pit mode sets the VTX to its lowest output setting, so a couple of watts so it doesn't cook. After you've done that, now click save. When you're flying, there's some information that you should see in your goggles, like your battery voltage. So we're going to head to the OSD tab to configure it to your liking. Here are the key things I have in my OSD. Once you're happy with the configuration and where everything is on the screen, press save and we're going to head to the video transmitter tab. For the VTX, you're going to need to download the VTX table from the manufacturer's website or head to the VTX tables link in the description. They're going to give you the default ones. If you're using the SpeedyBee TX800, the last two values are actually wrong, so you need to change them. What we need to change is the label of power level 4 to 600 to match the output power, and the value of power level 5 to 800 to match the label. Press save and then go grab a LiPo battery for the next step. Time for a video test. Plug in your LiPo and then navigate to a different tab and then back to the video transmitter tab. On the right in the VTX values table, it should have yes for device ready. Then, if you've got your goggles handy, pop them on and to check you see have video and the camera and VTX are all working. Now, the VTX does get super hot when we're on the bench, and since we still have a bit of work to do with the battery plugged in, turn it to pit mode and then press save, as this is going to stop the video from cooking, or at least it's going to cook it on a low heat. To help the manufacturer comply with radio transmission laws, some VTXs come limited in regards to the output power that they can produce, as well as the channels that they can access. Or this is also known as a VTX being locked. For the SpeedyBee TX800 to unlock it, you need to hold down the button on the VTX for 10 seconds, which then the lights are going to blink. After, you can set the video channel through Betaflight, hit save, and it should change channels in your goggles. The next two tabs are really important to be able to get your quad to fly. So if you have an ESC or stack with BLS in the name, we're going to need to close Betaflight and head to escconfigurator.com on our web browser. If you have one that has BL32 in the name, you can go take a bathroom break or grab a beer. In our web browser, we're going to hit connect and then select Betaflight from the pop-up. Then hit the read settings button, and now we're going to flash all ESCs with BlueJay, so we're going to hit flash all. Then we're going to select BlueJay from the firmware tab, leave the ESC selection as it is, and then select the latest firmware version as well as 48 kHz PWM frequency. Now click flash. It's going to take a while, but after it's done, we're going to head to the common parameters and set motor timing to 15 degrees on medium and leave everything else. Now it's time to hit right settings, and that's it. Disconnect the drone. You can now unplug your battery for a few moments, but keep it handy because we're going to need it. To get your drone to fly great, we're going to need to tune it. And tuning can actually be quite difficult, and it's an art form in its own. But Betaflight does have a trick up its sleeve, so we're going to head back into Betaflight and go to the Presets tab. In the Presets tab, the first thing we're going to do is type in your radio link. For me, I'm using ExpressLRS, so I'm going to type that in. I also fly Freestyle at 150 Hz packet rate, which is not the fastest, but it's not the slowest, but it gives me what I think is the best bang for buck in terms of range, penetration, and speed. So I'm going to select ExpressLRS 150 Hz, and then in the drop down, I'm going to select HD Freestyle, and then press the pick button. Now, tuning can also be difficult to learn, so Betaflight's made that really easy. All we need to do is type in Superfly, and then select the Superfly FPV 5-inch preset. Select RPM filtering, and then whatever you're using, whether it's 4S or 6S with a GoPro or action camera. So I'm going to be selecting 6S LiPo with HD cam. Again, hit the pick button, and now we can press save and reboot. We now need to configure our motors to make sure they're all working correctly, so head to the motors tab. If you remember earlier when I spoke about gyro and PID loop frequency, remember 8K, 4K, 3.2K? Well, here's where all that information comes in handy. If you have an F7 processor where you could have set that gyro frequency and PID loop frequency both to 8K, here's where you're going to set the ESC and motor protocol to DShot 600. And for any other setup, we're going to use DShot 300. For bidirectional DShot, turn that on. And for this build, I'm going to be running props out, where the front two props spin away from the camera and the rear two props spin away from the antenna. So we're going to tick motor direction as reversed and then hit save and reboot and come back here to the motors tab. The next few things that we do inside the motors tab should stop your quad from flipping out when you try to take off. Well, assuming everything else is correct. We now need to plug in our LiPo and then click reorder motors. We're going to hit I understand risks and then we're going to click start. Betaflight is going to spin a motor, and then all we have to do is select the motor on the picture that's spinning on our quad. Easy. Now I'm going to hit save. We also need to make sure that each of the motors spin in the right direction. So click on motor direction, I understand the risks, wizard, start/spin motors. And then simply for each motor, make sure it's spinning in the direction of the arrow on the screen. I use my finger to feel which way the motor is spinning, and if it's the wrong way, I simply click on the number to make sure it's spinning, and do this for all 4 motors. Once they're all spinning in the right way, you can then hit stop motors, remove your LiPo, and disconnect. Now, we've built a great quad, but before we can take it out to fly our maiden, there's one important step we must do before we put the final pieces on, and that's to give it a test arm. So disconnect your quad from Betaflight and power on your radio. Plug in your LiPo, and once you can see they're bound, we're going to hit the arm switch and make sure all the motors spin the right way. Often when we're doing this on the bench and we give the quad just a little bit of throttle and then back to 0, the motors are just going to ramp up, and they're going to continue to ramp up. And this often freaks people out, but this is actually normal, and it's just air mode in Betaflight doing its thing, which is exactly what it's meant to do. So if this is all good and all the motors are spinning the right way, it's time for the final assembly and one of the last but most important steps. Put the top plate on using the M 2.5mm screws that are going to go on the rear standoff, and then take 4 M3x8mm screws for the middle 4 bolts, and then grab the GoPro mount and the screws out and put them on the front. Then time to add the FlyFish-RC branded battery pad, battery straps, and it's now time to give this bird some wings. As I mentioned before, I'm flying props out, and this only clicked for me a few months ago about how to put props on correctly without having to double check each time. So here's how I do it. See, props have a high side and a low side. Whichever the high side is on, well, that's the direction the prop is designed to spin. So when I'm running props out, the front left arm gets a prop with the high side on the left. And then the arm that's diagonally opposite gets a prop that is designed to spin the same direction. The prop with the high side on the right goes on the front right arm, and then the same prop diagonally opposite. After your props are on, time to keep them secure with your prop nuts and tighten them down. And after that, it's time for the final and most important step in this build, which can save you from mid-air disaster and all your hard work going to waste. When I did this, I actually found I had some risks that I needed to take care of, and I was glad that I found them. And you know what this is? It's tightening every screw and checking every screw is tight. Because I actually found there was a few that were still a little too loosey-goosey, so I'm glad I tightened them up. Now the build's complete, and it's a beautiful summer's Australian day, 30 degrees, and it's only 11 o'clock. Not a cloud in the sky. I'm going to strap a GoPro to this